Hello, this is Ryan Woodward recording a demo and walkthrough for Intel's Digital Logic course. This is Lab 4 Part 2 of counters. And in this portion of the lab, what we needed to do is build a counter. And rather than using memory circuits like flip-flops or latches, we needed to implement a sequence like this. And this is essentially using registers in code that we would just simply increment and assign that incremented value to our counter variable. And that ends up getting assigned to the output, which is here. It's actually a 16-bit output, and we can see that our intermediate signal here, counter, is also 16 bits. And although this code supports 16 bits, which would be a total of 4 7-segment displays, I am not going to demo pressing a button until we get to enough values where we actually see digits in all the hex displays. But I will show, one, the code is compiling, but I will show that the 7-segment display, I took a lot of time to actually write out all of the 16 bits that are used for each possible state, all the way up to whatever it would be in well into the thousands. But for each of them, the 7-segment displays that are not in the ones place, I have zeros up until, for instance, if we hit 10, then we will see a 1, or a 1 in the tens place, and we don't see that. That doesn't change nearly as much as when we're counting in the ones place. So I don't bother to do much more than that, and I won't show much more in the demo, but I at least wanted to show that for this code we have now 4 7-segment displays, obviously 7 each because they're 7-segment displays. And we leverage that in this architecture here. We can see that we have 4 of them, and we see that we assign those 4 here. And we port map that, and I will show that it does count properly. Actually, this counting doesn't, it seems to skip, which is kind of okay, so that I can show that it actually goes through a lot of the numbers. There will be some adjustments made, but for now, this works just fine. And aside that, there's not much to talk about other than pointing out that we do have a reset. It is asynchronous, so we do have to clock it. Or excuse me, it is synchronous, so we do have to clock it. Rather than say the way I've traditionally done it, we just flip a switch and that resets it for us. And that seems to have some other issues in logic as well, where if we are clocking the reset with the enable high, then we can have some issues, but that's a different story. But for now, this is the VHDL, and if I have time, I will make a Verilog circuit, a Verilog version of this, but for now, this is the VHDL. Alright, here is Lab 4 Part 2, our counter with registers. So we have our reset switch here. If we wanted to reset that, for instance, we'll just press him up and then clock the reset, and it'll go back to 0 for us. But from there, we can continue to count items, and you will notice that mine skips a lot. There's some bugs I need to figure out, but for demonstrating the 16-bit, I think it's pretty good. But this is generally the idea, that we will increment the register, and we will go from there. All right, that is it for now. Thank you.